Good morning, everyone, and welcome to Emerald Ash Borer University. This is Robin Usborne from Michigan State University. My EAB University colleagues are Professors Cliff Sadoff and Elizabeth Barnes from Purdue University and Amy Stone from Ohio State University Extension. And we are happy to share with you today's webinar entitled The Economics of Area-Wide Ash Surveillance, Treatment, and Removal Strategies to Slow the Spread of Emerald Ash Borer in Urban Forests, presented by Bob Haight, a research forester with the USDA Forest Service Northern Research Station in St. Paul, Minnesota. Bob is a 30-year veteran of the Forest Service Research Station and an agency authority on the economics of forest management and conservations. Since 2010, he has published several influential papers on the economics of managing non-native forest insects and diseases, including the emerald ash borer. Today, he will be talking about the economics of ash tree management in cities. We have, for access to publications related to today's talk, please visit Bob's website. The link I will share with you in an email that you will receive from me tomorrow. So, and I will double check it. Someone has said that it doesn't go to the correct spot. So I will check this and make sure we have the right link for tomorrow that you will receive tomorrow. To our participants today, we welcome your questions and comments. Please type them in the Q&A feature or the chat pod, and we will respond to them after the webinar presentation. As I mentioned earlier, tomorrow you will be emailed a link to a short, voluntary, confidential survey that we hope you'll take the time to fill out. It helps us bring these free educational webinars to you. The email will also include our presenters' contact information, as well as information on how to obtain CEUs for viewing this live webinar. This webinar is being recorded and will be available for viewing later on the EAB University page of the www.emeraldashborer.info website. Thank you everyone for attending today. And Bob, please unmute your mic and you can begin your presentation.
Okay. First, Robin, I'll do a sound check and make sure that you can hear me okay.
Yes, you sound great.
Okay, great. Well, thank you for that nice introduction, Robin, and good morning, everyone. It's great to be here. I want to send out a quick shout out and thanks to Cliff Sadoff for inviting me to speak today. And also thank you everyone for listening in. What I'd like to do is share two of my projects on the economics of emerald ash borer management in urban and developed areas. I'll speak for about 30 to 35 minutes and then have plenty of time for questions. So the first project that I'll talk about addresses the question, what are optimal management strategies for surveillance, treatment, and removal of ash trees in cities? We address this question by building models for ash dynamics in cities that are subject to EAB infestation and applied those models to cities in Minnesota, New Jersey, and in Canada, Winnipeg, Canada in particular. Our results address quandaries facing urban forest managers, such as whether to invest in surveillance, whether to treat healthy looking ash trees with insecticides to protect them, whether to offer rebates to homeowners to treat their trees, and whether to cooperate with neighboring cities in developing joint EAB management plans. Our take-home messages are as follows. First, we found that surveillance for EAB infestations is best applied immediately. Waiting to apply management actions risks the buildup of the EAB population, which causes more damage and economic loss later on. Once surveillance finds an infestation, the optimal strategy is to treat both healthy and newly infested trees in the vicinity of the infestation, and remove highly infested trees to prevent the buildup of EAB. If the manager is risk averse and wants to minimize the likelihood of extremely damaging and costly outcomes later on, then the best strategy is to monitor the ash trees and remove ash trees that are found to be infested immediately. Significant gains in net benefits can be attained by managing private ash trees together with the public ash trees in the city. Furthermore, significant gains in net benefits can also be attained by cooperating with neighboring cities in developing EAB management plans. The second project that I'll talk about addresses the question of how can we design landowner incentive programs for managing emerald ash borer. And what we found is that a government program that reimburses landowners based on how many trees they treat with insecticide and protect will result in higher net benefits for all. So I like to introduce my talks with a map that shows the current extent of the EAB infestation. Because of its extent, EAB is one of the most economically and environmentally damaging invasive species ever to reach the US. As a reminder, EAB is a wood-boring insect native to Asia and accidentally introduced into North America in the early 1990s, probably in crating or pallets or dunnage made from infested ash wood and used in shipping. Since its discovery near Detroit in 2002, EAB has spread widely and killed untold millions of ash trees throughout the eastern United States, and now heading into the west in Colorado. It's increasingly likely that EAB will functionally extirpate one of North America's most widely distributed tree genera, the Fraxinus genera, with devastating ecological and economic impacts. Some of the most extensive damage of EAB is in cities where the insect kills ash trees along streets and in people's yards and parks. In response, an integrated management strategy called SLAM was recently developed to address EAB infestations in cities. SLAM was developed as a collaboration among Michigan universities and agencies, including APHIS and the US Forest Service. The goal of a SLAM project is to slow the onset and progression of ash mortality by slowing the growth and spread of EAB populations. SLAM management includes surveillance to find infested trees, coupled with insecticide treatment and tree removal within and around the infested area. Surveillance involves sticky traps, visual inspection of ash trees, branch sampling to expose the phloem and look for larvae. Surveillance is important because newly infested ash trees are asymptomatic, while they foster production of EAB adults that spread to neighboring trees. The most common systemic insecticides include emamectin benzoate, which is injected into the base of the tree in the spring, and then translocated via the xylem to canopy branches and leaves, where it kills both adult and larval EAB when they consume the tree parts. Studies have shown that this insecticide treatment provides at least 2 years of nearly 100% control of EAB, provided that the tree is in the early stages of infestation when it's treated. In addition to insecticide treatment, the other management option is to remove infested ash trees before the EAB adults emerge, and thereby reduce the spread of the adults into neighboring ash trees. In a study of the economics of SLAM, beginning in 2016, I led a team, including my colleague Esra Buyatakakan and EAB University from New Jersey Institute of Technology, and Kathleen Knight from the Forest Service, to address the question of what are the optimal strategies for surveillance, treatment, and removal of ash trees in cities. We co-produced this work with city foresters and tree care professionals in the Twin Cities, including folks from Rainbow Tree Care. We first needed a model to project ash damage and mortality in the city, and so we constructed a stage class model of ash population dynamics subject to EAB infestation. So this formulation is important because it assumes that the detectability of an infestation and the efficacy of treatment depend on the level of the tree's EAB infestation. And this is a really important point because no other ash tree projection model allows for these really important parts of the dynamics of EAB and ash. These features are important because EAB may infest ash trees for 1 or more years before the damage is visible. And furthermore, chemical treatment is effective only for ash trees with low or moderate levels of infestation. So I'm going to spend a few minutes talking about the features of this model and how it works and our validation of the model. And then after that, I'll describe how we applied it to emerald ash borer management problems in different case studies. The stages of ash health include susceptible trees, represented by this S, that are prone to infestation. And then we have 4 crown classes that represent different levels of infestation. The 2 lower levels represent trees or include trees that are asymptomatic. In other words, their crowns show no damage or very little damage. The 2 higher classes have increasing levels of infestation and visible crown damage. The population of trees in a neighborhood is fully described by the numbers of trees in the susceptible and these 4 infested tree classes. Each period, trees in each infestation class transition to the next infestation level, represented by these dashed lines. Trees in each infestation class produce EAB adults, which then may infest nearby susceptible trees, and which then transition to the first infestation class, represented by this line here. The model is stochastic because the number of newly infested trees is uncertain and depends on the total number of EAB adults produced in the neighborhood and in adjacent neighborhoods. Because the number of newly infested trees is uncertain and newly infested trees are asymptomatic, the surveillance is required to estimate the number of trees in each infestation class. Here, surveillance is assumed to take place in period 2, and the shaded boxes represent known numbers of trees in each class, which are found during the monitoring process. Following surveillance, the manager may treat or remove trees from various infestation classes. Susceptible trees and trees in the 2 lowest infestation classes are asymptomatic and may be treated with insecticide, which kills any larvae and prevents infestation for 2 years. The treatment is represented by these green lines, which show the transition of trees from infested to susceptible classes 2 years hence. Trees in the 3rd infestation class have visible damage and are irreversibly infested. Those trees may be allowed to stand or may be removed to reduce EAB spread. Removal is represented by these solid black lines. Trees in the fourth class are assumed to be almost dead and must be removed because of their hazard. Down here. So we calibrated and validated this stage class model using 7 years of observations of ash mortality and plots in northern Ohio, maintained by my Forest Service colleague, Kathleen Knight. These 9 graphs compare model predictions of ash mortality versus observed ash mortality in plots in the vicinity of Toledo. Based on statistical tests and visual comparisons, we concluded that the model provides a valid representation of ash dynamics subject to an infestation over a 5 to 10 year horizon. Next, we applied the optimization model to managing an ash population. And in this case, I'll discuss our study in Burnsville, Minnesota, which is a suburb of Minneapolis, south and west of Minneapolis, where an EAB infestation was suspected to be present in 2017. We determined the optimal sequence of surveillance, treatment, and removal actions to maximize the benefits of healthy ash trees while staying within the available city budget. The time horizon was 5 years. Our results address 2 quandaries facing the city manager: whether to invest in surveillance and whether to treat healthy looking ash trees without that are present there. We found that surveillance is best applied immediately. Waiting to apply surveillance and management risks the buildup of the EAB population, causing more damage and economic loss later on. Once surveillance identifies a new infestation, the optimal strategy is to treat healthy and newly infested trees in the vicinity of the infestation and remove any highly infested trees. If the budget isn't sufficient, then priority should be given to treating newly infested trees while postponing the removal of highly infested trees until they die. This optimal strategy provides significantly higher net benefits than do strategies based on rules of thumb, including staged removal of the ash trees, monitoring and removal of ash trees, and just random treatment of a proportion of the ash trees in the city. Next, we also revised the model to the optimization model and applied it to a situation in which the city forester is risk averse, meaning that the forester wanted to manage the ash trees to reduce the likelihood of extremely damaging and costly outcomes later on. We found that the optimal solution for a risk-averse manager is to monitor and removal strategy. A risk-averse manager should survey often and remove ash trees when they're found. We discovered that insecticide treatment in this situation for a risk-averse manager is not advised because removing ash trees over time avoids the possibility of catastrophic loss. So we applied these models, and based on these results, the city managers chose to monitor you and then use insecticide treatments and removal in the vicinity of found infested trees. And as a result, 5 years hence, they've had very slow progression of ash mortality throughout the city in comparison to the neighboring suburban cities where the ash mortality has been much greater. Now I'd like to switch focus to municipal cooperation. In 2012, I was part of a team that addressed the question of how much does coordination among cities for the management of EAB increase urban forest benefits? We used the Twin Cities as a case study because EAB infestation had recently been discovered in 2009, and because cities were independently developing management plans and setting budgets for EAB control. To assess the potential gains from cooperation, we first identified a 300 square kilometer study area encompassing Minneapolis, St. Paul, and surrounding communities. The study area was centered on the location of the initial EAB infestation in St. Paul and represented an area that we projected would be infested within the next decade. We divided the study area into 5 cities and applied our stage class model of ash dynamics. And we used the model to evaluate 3 different management strategies for the study area. The first strategy is called no action. Here, all 5 cities are assumed to remove ash trees when they were found infested. The second strategy is called local management. Here we assume that each of the 5 cities had different budgets for ash treatment and removal, and each city spent its funding to maximize the net benefits within its own boundaries alone, without concern for what its neighbors were doing or how any spillovers of EAB across city borders. The third strategy is called aggregated management, and here we assume that all of the funding available in 2011 across the cities in the study area was pooled and then spent to maximize the net benefits across all 5 of the cities. Our main findings were these. With no action, most of the study areas infested within 5 years, resulting in a loss of forest benefits of $300,000. With each city managing according to their local budget, the outcome isn't as bad as no action, but there is a net loss of forest benefits of $150,000, represented by the blue bar. Aggregating the budgets and coordinating management among the cities can more than double urban forest benefits relative to a strategy in which the city acts independently with a net present value of over $200,000, represented by this green bar. The take-home message is that a regional management and funding strategy would more effectively control the infestation than an inconsistent city-by-city response or no action. However, a regional strategy would require that cities pool their money and spend it according to what's best to slow the spread of EAB, which means that one city may be giving funding to a neighboring city for management outside of its boundaries, which is difficult. And so some of our current research involves looking at incentive structures for cities to share funds across their borders. An important issue in EAB management is the limitation of managing private ash trees. This is important because private ash trees often comprise a larger proportion of the urban ash population than do public ash trees. In our Twin Cities study, we looked at 2 different scenarios. One with 30% of the ash trees available for treatment and removal, representing the population of public ash trees, and another with 100% of ash trees available for treatment and removal, representing the population of ash trees on both public and private land. We used our optimization model to estimate ash survival and net benefits under each scenario. For the case where 100% of the ash trees were available for treatment, almost 90% of those trees remained after 5 years, and the EAB population was slowed considerably, represented by this blue bar here. The net benefits of this strategy were over $1 million. For comparison, for the case where only public ash trees could be treated, only about 50% of the ash trees remained after 5 years, and the present value of net benefits was substantially lower. This result emphasizes the importance of managing ash trees to slow the spread of EAB, of ash mortality in the city, and leads me to the next project. Working with my partners at the New Jersey Institute of Technology, we're addressing the problem of designing landowner incentive programs for the management of EAB in cities. There's growing interest in designing management programs that involve transfer and subsidy payments between stakeholders. And in our case, we wanted to design a reimbursement program in which the public forester offers a cost-sharing incentive to private landowners to manage ash trees on their properties. So the research questions include, how much should the rebate or subsidy be? Which landowners should be included? And how widely should the program be applied? Our hypothesis is that a well-designed incentive program will increase the capacity of government to reduce the damage of EAB with reduced costs in the city. We're building the model with input from city managers in various parts of New Jersey. So here's an example of a program in which the city reimburses the private landowner based on how many trees the landowner treats. At the beginning of the period, in period 1, both the city and the landowner have common knowledge about the number of ash trees on the property and the likelihood of ash tree infestation. However, neither the city nor the landowner know exactly how many of those trees are actually infested. Based on this information, the city offers a reimbursement schedule to the landowner up here, which lists the amount of the rebate as a function of the number of trees the landowner decides to treat, and it's payable after treatment takes place. The landowner then chooses whether to accept this reimbursement plan based on its projection of the revenue from reimbursement, net the costs of surveillance, treatment, and removal. If the landowner accepts the plan, the landowner identifies the infested ash trees and chooses the number of ash trees to treat to maximize its benefits based on based on its projection of the number of surviving trees at the end of period 2, which these boxes represent. The city reimburses the landowner based on the landowner's decision on how many trees to treat. The problem is that the city needs to set its reimbursement plan for each landowner to maximize the net benefits to the city, given its knowledge of the optimal actions that the landowner will take as a function of this reimbursement schedule. So as I said, the problem is to design the reimbursement schedule. And we found that the optimal reimbursement schedule depends greatly on the current infestation rate, the cost of treatment, and the landowner's value of healthy trees. For example, let's say a landowner has some infested trees and uninfested trees, but as a city forester, I don't know how many, but I know that the infestation rate is relatively low. In this case, it's best for me to, sorry, my phone was ringing there. In this case, it's best to encourage the landowner to treat all of the infested trees, however many there are. If the cost of treatment is high relative to the removal cost, or the landowner doesn't value healthy trees very much, a rebate may be needed to encourage ash treatment. The amount of the rebate increases with the number of infested trees. If the cost of treatment is low relative to the removal cost, or the homeowner values healthy trees a lot, very highly, then no rebate may be needed because the landowner will treat the trees with money from its own pocket. So in this case, the problem is to tailor the rebate based on the number and size of the landowner's ash trees so that the landowner ends up treating all of them. Our future work in this area of reimbursement scheduling includes scaling this rebate model up to the neighborhood and city level. So we need to define different types of landowners based on the number of ash trees that they have and how they value those ash trees and the likely infestation rates. We also need to prioritize landowners in neighborhoods for including them in the incentive program, given that the city has a limited budget for incentives. We need to determine the optimal allocation of the city's resources to manage the public ash trees through the city's forestry program and managing the private ash trees through the incentive program. And then we'll be setting up case studies working with selected municipalities in the state of New Jersey, which was recently infested with EAB in 2014. So that concludes my discussion of the case studies, and I want to end with a slide that summarizes my take-home messages. So the first study that I shared addressed the question of what are optimal strategies for surveillance, treatment, and removal of ash trees in cities. With modeling and with applications to cities in Minnesota, and we found that surveillance is best applied immediately. Waiting to apply management actions risks the buildup of the EAB population, which causes more damage and economic loss later on. Once surveillance finds an infestation, the optimal strategy is to treat both healthy and newly infested trees in the vicinity of the infestation and remove highly infested trees to prevent the buildup of EAB. If the city forester is risk averse and wants to minimize the likelihood of extremely damaging and costly outcomes, then the best strategy is to monitor the ash trees and remove ash trees when they are found to be infested. Significant gains in net benefits to the city can be attained by managing private ash trees together with public ash trees. And significant gains in net benefits can be attained by cooperating with neighboring cities in developing EAB management plans. The second study that I talked about, that I shared, was how can we design a landowner incentive program for the management of EAB in cities. Here we found that a government program that reimburses landowners based on the number of trees, ash trees, that they treat will result in higher net benefits for all. So that concludes my presentation. And now I'd like to thank you for listening and take any questions that you may have. And I think I'll turn it back over to Robin to manage the question part of this talk.
All right, thank you so much, Bob. We do have a few questions. So Cliff is asking, can you please describe how you monitor the trees in the surveillance program? You mentioned using traps, visual sampling, and branch sampling as common methods. Must you use all three?
No, in the cases that, in the Burnsville example case, visual sampling was the most common, visual surveillance was the most common approach. So the city foresters and the tree care professionals would, well, first, I'll take a step back. First, there was significant effort put into mapping the location of the public ash trees. And that was shown in the picture of Burnsville, where the red dots showed each tree's location. And then for surveillance, the city forester would basically visit those trees and look for signs of woodpecker damage or branch dieback in the upper levels of the canopy. So it's not a very costly kind of approach. They also did apply some girdling especially in the parks, to see of selected ash trees to see if they could attract see if those girdle trees attracted emerald ash borer. But in our case in the Twin Cities, branch sampling wasn't employed because of the costliness of it. But branch sampling in another example where we consulted with the city managers in the city of Winnipeg in Canada, branch sampling is a pretty commonly used technique there.
Okay, could you elaborate on how you describe failure from the standpoint of a risk-averse urban forester?
Right.
How does visual removal of all ash trees after monitoring and removal be less of a catastrophe than a project that saves ash trees through chemical control?
Right. That is an excellent question. So the way we define an extremely costly or damaging outcome, it's one in which a large portion of the ash trees become infested and die quickly or die, so that in those situations the city would have to respond with a large program for tree removal all at once. And so those scenarios are pretty rare because it would require a scenario like that would require rapid growth of the EAB population. It would require a situation in which surveillance wasn't applied or wasn't effective, so that many trees were infested that were not known about. So in that situation, to avoid those kinds of situations, a manager would, for one, monitor the ash trees regularly, and then remove ash trees when they become infested. And the reason that is better is because the ultimate goal would be to basically remove the entire ash population over time, which by default would reduce the possibility of catastrophic loss. And so basically what our model was doing was providing some justification for the staged removal strategy that, like the city of Minneapolis was doing, where they just wanted to schedule the removal of their ash populations over a fixed period of time. The strategy that we found with our modeling wasn't as extreme as that strategy. Instead, it was more about removing the ash trees only when it was about monitoring the ash trees carefully and removing the ash trees when they're found to be infested, rather than investing in treatment and maintaining the ash population over a longer period of time.
Okay. Raphael asks, how are the costs of surveillance calculated?
Right. So the cost of surveillance we calculated based on the amount of time that a person spends examining a tree. So we we assumed that a tree, that a person would spend 20 to 30 minutes on each tree and move down the block. So we just calculated how many trees per hour a worker could examine, and then what the wage would be for that. So visual examination is the least costly of the surveillance methods that we looked at. Branch sampling, on the other hand, is much more expensive because of the time it takes to climb the tree, remove the branch, and take the branch, and then remove the bark from the branch and look for larvae.
Come on. Okay. I'm having trouble unmuting here. Phil Marshall says, I may have missed this, but did the municipalities use ordinances to implement ash management?
Not in the ones that we worked with. Like the city of Burnsville did not use ordinances to. The city of Burnsville focused primarily on its public ash trees management, and then it contracted with a tree care provider to make ash treatment and removal available to its private landowners. And then in that contract, the tree care provider was willing to give a price break for the insecticide treatment to private landowners who elected to use it.
Okay, on that same vein, Elizabeth asks, in places where EAB has already killed a lot of trees, we often get questions about whether the state or city will pay for tree removal. These dead trees are very dangerous, but the cost of removal is often too high for some people. Do you know of anyone who either has or is studying cost sharing or other methods of lightening the burden of dead ash removal on the private landowners?
Right, Elizabeth, that's a good question. And well, we, in working with doctors Buya Takaya and Dr. Kay at New Jersey Institute of Technology, that's what we're trying to do, is to look at the economics of different kinds of incentive programs. And I mean, what we hope to find is that that we can design programs that are cost effective for cities. So I don't know of other people researching this problem at the moment. I think the challenge will be to convince city managers who are cash strapped to implement a cost share program, because it's going to, it's going to cost. So they have a choice, do they spend their limited money on managing their public ash trees, or are they going to use a portion of their funds to incentivize private landowners to manage or remove dead ash trees? And that's going to be a question that city planners have to address. It's a tough one.
All right. Andrew Leopold says, Bob, this is beautiful work. I have a few questions about the first SLAM model you presented. One, it wasn't clear to me what you assumed about the detectability of infested trees, but the reality is that many trees may show little or no symptoms. Furthermore, there are typically large numbers of trees in homeowners' backyards, and these cannot be seen by ordinary tree surveys. Two, the spatial aspect of your model was not clear. Was the model spatially explicit, and what did you assume about spatial contagion of tree colonization over time? Also, were there any assumptions about spatial distribution of surveys?
Hi, Sandy.
You got all that? Oh.
Yeah.
Okay.
Yes, Sandy and I have worked together a lot in the past, and I'm really pleased that you're here. Shout out to you. Yeah, so I'll start from the back and go for and say that the model was spatial. What I described as the stage structured model that would be applied to a neighborhood, then the city would be composed of many neighborhoods. And the neighborhood size would depend on how many ash trees are contained within it. In other words, there's quite a bit of flexibility in deciding how to subdivide your city into neighborhoods based on the ash tree population. So then within a neighborhood, we assume that, so the question is, I think you were asking is how does the spatial distribution of the ash within a neighborhood affect the movement of EAB among those trees? And so what we're subdividing the trees within a neighborhood into these 5 different crown classes. And then based on the number of trees in each class, we make an assumption about how many adults would then be moving from infested trees to uninfested trees within that neighborhood. So that's one assumption. And then the second assumption is that we also account for the movement of ash trees between, the movement of EAB between neighborhoods. So some EAB will move from one neighborhood to another. In other words, they don't have to stay in one place. And we have assumptions about the proportions of EAB that move within the neighborhood and between neighborhoods based on EAB movement data. So that I think addresses the spatial question. And I think at the beginning there was a question about surveillance. And so can you ask that question again? Because I think it was, I don't think I quite remember it.
Okay, let's see. It wasn't clear to me what you assumed about the detectability of infested trees. Is that what you're saying?
Right. Yeah.
Okay.
Okay. I get it. Yeah.
Okay.
Yeah. Yeah. So Sandy's asking about the detectability. And so we assume that in this model that the detectability is essentially 1. In other words, if a tree is visually inspected, then if an EAB was present, it would be detectable. So that's a probability of 1. And that makes surveillance quite cost effective because there's basically, we assume that there's no mistakes. And obviously that is a heroic assumption. And I imagine that if we reduce the detectability of the survey method in our model, then we would find that surveillance would be less cost effective, and that it would possibly make ash management more difficult and more costly, and tip the scales more towards the ash removal rather than treatment. In other words, it would be better, one would be better off to begin to remove your ash trees over time. In other words, if it costs a lot of money to find where the infestation is in its early stages, then it's going to be probably better to more cost effective to just wait until the ash trees show infestation. But then at that point, they're not really favorable to treatment, and so they have to be removed. So it's kind of a trade-off in terms of the detectability and cost of the surveillance method. But we're assuming that, and this is from our experience in the Twin Cities, we feel pretty confident that we can find through visual inspection the presence of EAB at a stage in which the tree is still can be treated effectively. Okay, and then there was a question in the middle there that I can't remember.
Okay. Let's see. Okay, there was the spatial aspect of your model was not clear. Was the model spatially explicit, and what did you assume? Is that the one you're looking for?
Yeah, no, there was something about trees in people's backyards or something, but maybe that was part of the first part of the question.
Yeah, that was part of that first one.
Okay.
So you're good.
Yeah, okay.
Okay. Elizabeth says, separate question. You mentioned that it is difficult to do cost sharing between cities, but that this is often more effective on the whole. Is this something that states or provinces could help facilitate, or are there governmental structural issues with that?
Right, yeah, absolutely. I think that there needs to be a higher level of authority to incentivize cooperation. So, for example, in Minnesota, there's either the state government or a regional authority, like in the Twin Cities, we have a sort of a Twin Cities Planning Commission that has a fair amount of authority and requiring cooperation, say among cities for transportation and emergency service provision. So those organizations could equally likely incentivize cities to work together for managing their urban forest infrastructure, their urban forests. Let me say one more thing. There's also a council of mayors in the Twin Cities that meet regularly and discuss issues associated with their cities, including emerald ash borer. And yeah, and so organizations like that could be lobbied or incentivized in some way to work together. On that front, there hasn't been any, even though those organizations exist in the Twin Cities, they haven't been successful in, cities tend not to want to share funding or resources with each other. And so it hasn't happened for EAB management. However, what has happened is that tree care companies have filled the void and have created kind of generic management plans that they sell to cities. And so they contract with cities to undertake these management plans. And since the management plans tend to be fairly similar from one city to another, there's sort of this de facto cooperation taking place. So it's one where a private enterprise has come in to fill the gap of government-wide cooperation.
Okay, Jacob has a comment here. He says the local electric utility will help with the dead or dying ash trees if it's near their power lines. I also have one question here from John that said, is the assumption of functional extirpation of ash premature? Can judicious protection of some ash prevail?
Oh, that's a great question. Yeah, so there's a lot of work being done on that question. And so let me start by saying that within the Northern Research Station and the Forest Service, there's a really active ash breeding program starting out in Delaware, Ohio with Jennifer Cook. The idea is to identify ash survivors or ash trees that survived the initial wave of EAB and take cuttings from those trees back to the lab and see if they are preferred or not by emerald ash for larvae or adults in the lab. And then for the trees that are verified to be less tasty, I guess, I don't know how to describe it, to the EAB, then those are candidates for trees that may have some kind of resistance. And then research is beginning on trying to understand what resistance involves, what the mechanisms of resistance are. And then also those trees are being used in nursery studies to try to speed up the reproduction and breeding of ash trees that have resistant traits. So the hope is that just like the work that's been done in developing elm trees that are resistant to Dutch elm disease, that we'll be able to develop ash trees that are resistant to emerald ash borer. And then, you know, in the most optimistic scenario is that those varieties of ash could then be used in restoration strategies in the ecosystem. So I guess in a long story short is that ash trees, functional extirpation is a bit of a sort of it may be exaggerated at this point. The other thing I'll mention is that that in talking with Kathleen Knight, who's an ecologist with the Forest Service, she says that some ash trees that have died have been sprouting back, and so that there's in the aftermath of an infestation, ash will grow back, and it's unclear what the long-term ecology will be of restored or naturally regenerating ash trees, and whether the emerald ash borer will come back in successive waves or what. So there's still a lot to be understood in terms of the ecology of ash in the eastern forests.
Well, Bob, thank you very much.